Hello and welcome to today's video. You will have noticed that we've talked a lot about integration, but not about actually computing integrals of functions. That will change today in this video, because in this video we're going to lay the groundwork for finally being able to easily compute integrals. You will surely have noticed that the definition of an integral is nice from a geometric point of view, but not from a computational point of view. It seems very hard to actually compute an integral using that definition. Luckily, there is a different way, and we'll discuss that different way today. And this different way is known as the fundamental theorem of calculus. And as easy as it may seem, it is really one of the most fundamental connections in calculus ever. So this section is titled Antiderivatives and the Fundamental Theorem of Calculus. And as I said, the question, the motivation for all this is basically the question, how can we actually compute integrals in practice? Now, that fundamental theorem consists of two parts. We write those down as two different theorems. The first part is the following. Let's say we have an interval as usual. So I subset of R be an interval. Let f be a function on that interval. And what we need in addition to integrability is the function needs to be continuous. So we want a continuous function on I. And let A be an arbitrary point in that interval. Then we can define a new function. And this function looks like this. We define a function capital F that also is defined on the domain I. And this function is defined as capital F of x is the integral from a to x, so x appears in the boundary, of the function f of t dt. And of course that definition is valid for any x in the interval I. And what the theorem now says is this function is differentiable and what's more, the derivative, capital F prime of x, is exactly f of x. So we define a new function, and through derivatives, we get back the original function. That is basically the most important part of the fundamental theorem of calculus. Now, why is that useful for integration? Well, of course, we know how to differentiate a function. So basically, we can use this connection here. We can compute integrals of this form if we are able to find a function that differentiated is equal to our integrand. And as we know how to differentiate functions And as this differentiation follows certain mostly easy rules, for many, many functions, it's easy to come up with a function that satisfies this. Now, before we go deeper and if we see the second part of that fundamental theorem of calculus, let's try to prove this. And actually, with the help of the tools that we have already collected, this proof is not going to be difficult. So let's consider a point x star, and we want to compute the derivative of capital F at that point x star. So let x star be a point in I, and h in R. And of course, h will later tend to 0, so you can imagine h is a very, very small number. What we want to do is we want to first express the difference of capital F of x star plus h and capital F of x star. That is going to be part of the difference quotient, and the limit of the difference quotient is, of course, the derivative that we're looking for. So let's first express that difference. Then, by definition, f of x star plus h is the integral from a to x star plus h over f of t dt. And f of x star is the integral from a to x star over f of t dt. Now, using the properties of the integral, we can combine those and write that as the integral from x star to x star plus h of f of t dt. So now looking at the difference quotient, f of x star plus h minus f of x star divided by h. This is then, of course, just 1 over h times this integral from x star to x star plus h f of t dt. Now, for that integral, we want to connect this with a value of the function f itself. And the one tool that we have for this is the mean value theorem of integration. So let's have a look at that. According to the mean value theorem of integration, there exists a point in the interval that we integrate over, so in this case between x star and x star plus h. So we call this point x tilde, between x star and x star plus h, and h could be negative, so x star plus h could be the left boundary of the interval, or it could be positive, then x star plus h is the right boundary. That's why I'm not writing the interval here, but the point is between those two, such that the following holds, such that we can express that integral x star to x star plus h over f of t dt as the area of a rectangle. One side is simply the interval, so the length of the interval between x star and x star plus h, and that is, of course, h. And the other side is given by the function value at that point x tilde. So we can express that as f of x tilde times h. And recall that the mean value theorem of integration holds for continuous functions f. So this is why we need continuity in our statement of the theorem here. Okay, so this is true according to the mean value theorem of integration. And now, if we use that here, then that means we can just continue with that expression here. Let's copy that. Put it in here. And that means we just replace this expression here by this. So what we get is 1 over h times f of x tilde times h, or just f of x tilde. And now what we do is we let h tend to 0. Now f is a continuous function. As h tends to 0, of course, the points x star and x star plus h get closer and closer together, or in other words, x star plus h tends to x star. And x tilde is between those two. So x tilde also will tend to x star. Okay, so for h to 0, we have x star plus h tend to x star. So x tilde will tend to x star, as remember x tilde is between those 2 points, x star and x star plus h. F is continuous, so the limit of f of x tilde is exactly equal to f at the limit of x tilde, which is x star. So as f is continuous, the limit of f of x tilde for h to 0, and remember x tilde depends on h, so that is why this limit makes sense. Well, that is exactly equal to the function value at the limit of x tilde, and that is x star. So this is going to be f of x star. And altogether, what that means is the derivative of capital F at x star, that is given, if it exists, by that limit of capital F of x star plus h minus f of x star divided by h for h to 0. And we have just shown that this is equal to f of x tilde, and as h goes to 0, f of x tilde goes to small f of x star. So this proves the fundamental theorem of calculus. Now, because functions of that type are so important, they get a name. Basically, what we do here is, what it says is basically that integration is the reverse operation to differentiation. So these functions capital F get a name, and that name is going to be antiderivative. Let's write that down as a definition. So, as usual, let I subset of R be an interval. And let f be a function on that interval. So f is a function with domain I and values in R. Then a function capital F that is also defined on I and maps to R is called an antiderivative of small f. If the following is true, capital F is differentiable on I, and the derivative f prime of x is equal to small f of x for all x in I. So an antiderivative, as the name suggests, is the inverse operation to take in a derivative. As a remark, the antiderivative is not necessarily unique, or it's usually not unique. More precisely, if we have two antiderivatives of the same function, then they may differ by a constant. And this is what this remark says. So that f I to r be a function on an interval I. And let's say we have two antiderivatives, so capital F, capital G. Let those be antiderivatives of f. Then if we have a look at their difference, f minus g, and differentiate that, then this is, of course, due to elementary differentiation rules, this is f prime minus g prime. F prime is small f, and g prime is also small f, because they are both antiderivatives of small f. And of course, f minus f is 0. So the derivative of f minus g is 0. And that means f minus g itself is a constant. So two antiderivatives of the same function can only differ by a constant. And on the other hand, if you have one antiderivative of a function and add any constant to that, then of course you get another antiderivative. So the set of all antiderivatives is take one and add all possible constants to that function. And how do we use antiderivatives to compute integrals? And that is now the second part of the fundamental theorem of calculus. That's our next theorem here. That again says the same introduction as for the first part. Let I be an interval and that small f be a continuous function on that interval. So continuous function on I. Then if capital F is an antiderivative and an arbitrary antiderivative, doesn't really matter which one we choose. Of small f, then for any 2 points A and B in the interval, we have the integral from A to B over f of x dx is equal to the antiderivative, capital F, evaluated at B minus the antiderivative evaluated at A. And finally, that is how you can compute integrals. You determine an antiderivative, and that is usually possible using some guesswork and rules of differentiation, and it might be more complicated than just that, but at least it's a beginning. And once you have that, you can evaluate integrals by just evaluating the antiderivative at 2 points. These 2 points in the boundaries, to be precise. So this is how we can compute integrals easily, more or less easily. Let's also prove that. That's another nice and easy proof. Again, that of course all depends on the tools that we have developed so far. So let's define a function capital G of x as the integral from a to x of f of t dt. So that's the definition from the first part of this fundamental theorem. And that is an antiderivative. So that means there is a constant gamma in R, such that f is of the form g plus gamma. F and g are both antiderivatives of the same function, small f, so they differ by a constant, and that constant is gamma. Now that's the case, we can make the following computation. If we have a look at this expression f of b minus f of a that appears in that theorem, that is then exactly equal to g of b plus gamma minus g of a minus gamma. So plus gamma minus gamma cancels out. We're left with g of b minus g of a. And by definition of g, the first one is the integral from a to b of f of t dt. And the second one is the integral from a to a of f of t dt. So, well, the integral from a to a, that is, of course, 0. So we're only left with the integral from a to b of f of t dt, and that is exactly what we wanted. So we can compute this integral using an arbitrary antiderivative, capital F, of our function, small f. Now, finally, we have found a method that we can use to compute integrals, at least not too complicated integrals. Before we start doing that, before we see a few examples, one more definition to fix the notation for doing our computations. So again, as usual, I is an interval, so let I subset of R be an interval. Let f I to R be a function, and capital F I to R an antiderivative of small f, meaning, as in the definition, capital F prime is small f. Then, first part of the definition, we can consider the set of all antiderivatives of small f. The set of all antiderivatives of small f given by, well, that is simply the set of capital F plus gamma, and gamma is any real constant. So, as I said, you can get any antiderivative. If you have one, you just add arbitrary constants, you get all the others. And that set is called the indefinite integral of f. So one function that differentiated becomes f, small f, is an antiderivative. The set of all antiderivatives is the indefinite integral. And what is more important is that indefinite integral is denoted by the notation integral of f of x dx. So we just leave out the boundaries a and b, and that is why it's called the indefinite integral. So by that we mean the set of all antiderivatives. And that same notation is also often used to refer to an arbitrary element. So if you just want to say use one antiderivative, then usually you also use that notation. Yeah, that's not really precise, but you will often encounter that. So Let's make a note of that as well. The same notation is often used to refer to an arbitrary element of that set. And second, again, a notation, basically an abbreviation for denoting the computations that we make. So we frequently use the following abbreviations. Those abbreviations are, if we want to express the difference of an antiderivative evaluated at 2 points, then we usually write that as this antiderivative, capital F of x, and then we either use brackets like that and write the two boundaries on the right side here. Now that means that's an abbreviation for f of b minus f of a, and that of course is by the fundamental theorem of calculus, second part, that is the integral of f of t dt from a to b. And a different abbreviation that you'll also encounter frequently is f of x. And then you just draw a long line, and again you write the boundaries a and b on that line. And that also means the same thing, f of b minus f of a, or the integral. Okay, that completes this treatment of antiderivatives and the fundamental theorem of calculus. One of, as I said, one of the most essential theorems that you'll ever encounter. We'll see a few examples of how to apply that to compute integrals in one of the upcoming videos. And as usual, I hope I'll see you then.